Before we get started on this topic, you already know some things about decompositions if you've used singular value decomposition. And the history behind this dates back to a book from the early 70s by Gollum and Van Loan called Matrix Computations. And they directed people away from using the inverse of a matrix to calculate the least squares solution to linear regression problems. So today, almost no software actually does a linear regression problem by calculating the inverse of a matrix. It's doing the singular value decomposition because it's much faster and much more stable process. It also works with matrices that are less than full rank, where you have to drag out something like a pseudo-inverse to make everything work. The same thing holds for ridge regression, where you've got some nice formulas that are very similar to the ordinary least square or the ordinary linear regression case. So you've seen decompositions before. We're taking it essentially to the next level. So first, we need to talk about what is a tensor, and essentially you kind of already know this. You're essentially going from the linear algebra, vector spaces, on vector spaces to multilinear algebra on vector spaces, which a matrix is just a linear transformation between vector spaces. You're referring it to a basis when you write down coordinates. And in the same way, a tensor is a multilinear transformation between vector spaces. When you get all these indices, again, you're referring it to a basis, maybe the standard basis, which you sort of already know. Some people like to work with Rubik's cubes. You can also watch some videos on YouTube to get an idea of how to visualize this, essentially as cubes and slices through cubes and fibers of cubes. Fibers being the long, narrow little vector things, and slices being the face. So you've also got hypercubes in your data warehouse. When you talk about multi-hierarchical things in your data warehouse, then you're right there in that data structure. The things that we're going to be really talking about here are decomposition. Can you go to a lower rank structure? And that's really what you're doing with a singular value decomposition. You're taking a rank 2 tensor. Don't know how to get rid of that, but okay, there we go. You're really taking a rank 2 tensor, which is a matrix, and you're saying, I want to decompose it into a rotation, a stretching, and another rotation. And principal components then is another type of decomposition where you're trying to reduce the rank. Now, for rank higher than 2, this dates back to the 1960s and some other work that comes from chemometrics, which is to chemistry what econometrics is to economics, and also psychometrics, which is again what that's to psychology what econometrics is to economics. And a lot of people did work on this, and the mathematicians also did work on this, but in a very abstract way. So there's really two types of decompositions. The one we're really going to talk about is the sum of rank 1 tensors, which are vectors. We're just going to try and take products of vectors and decompose based on that. And then you can also do a multilinear PCA, which is definitely used in chemistry and other places. Now, as far as in machine learning, people are using this actively in feature discovery, recommender systems. When you've got multiple users and multiple items, you can phrase, you've got a natural multi-dimensional hierarchy. So using a multi-dimensional type of data structure here can help. People are also looking at time-evolving networks. And the 3 tensor there is they've got time as a factor, or time as a dimension, and they're looking at these complicated structures stacked up over time. So there are also interesting ways to apply this to topic modeling, which basically is an idea the idea that you've got a document, or you've got a collection of documents, you want to discover what are the topics. Well, you can't read all of them, and they're not tagged, so it's really kind of a non-supervised or semi-supervised method. And then the interesting thing is rephrasing some of these things can be made embarrassingly parallel where they weren't before. You can get some software for this. The Tensor toolbox in MATLAB is very widely used. There's some C++ code, in particular from the topic modeling people out in UC Irvine. And then Facebook has a project that they open source, TH++, which is a C++ library with a Python bindings for it. So you get both of those there. And then if you're partial to R, Tensor is a very is an actively developed package. And then Python has three packages of that are also possible for you to use. So there's ways to incorporate this in your work. If we let's take a look though at some things where you can learn more about this. Earlier in the year, there was a talk at the Strata conference in California that attracted some interest from the O'Reilly people, and that's why they published a couple of blog posts and a podcast. Last year, I think there were some talks at the MLconf in California from a couple of faculty, well, one faculty member, Amina Anandakumar from UC Irvine, and then from Sandia, Tamara Kolda, who Tamara Kolda essentially came to this from the Golub and Van Loan tradition, early 2000s, where the workshops where they really started developing these ideas in sort of a mathematical way and really trying to write them down carefully and providing some of the basic mathematical infrastructure that people are using today. There's also been some work from the signal processing side. And much of the computational methods have been come from the signal processing side and from this SIAM review paper, which is a lot more general and will give you a lot better idea of where things are used and some of the most common algorithms and their advantages and disadvantages. And then the first tutorial here on spectral and tensor methods for guaranteed learning. Well, what do we mean by guaranteed learning? Your cost functions in your machine learning problems are often non-convex and have many types of local minima. And essentially, if you run them twice, you may get a different answer. You may get a very different answer, basically because you're going to a different local minima. So tensor methods, however, enable you to get to the global minimum. And the way these tensor methods are used are avoiding the NP hard problem and going, by using tensor methods, you can avoid the NP hard problem, which you get by phrasing it as matrices. So you've neatly danced around that. And then the guarantee is, well, you always get the same answer. You go to the global minimum. It doesn't matter how many times you do it. So it enhances this whole idea of reproducibility that we really need in practical matters. So that's about 5 hours of videos, which you can use, which you can view, and gives you a good overview of how it's used in a setting where the general class of models are called latent variable models. So they're concerned with hidden variables of all types, not just topics in a document. And I'll just leave you with this. If you've got some data structures that are multidimensional, then you can start thinking about how you might want to put this in. I was thinking the other day about Nicholas Wirth's book from the 70s was Algorithms plus Data Structures equals Programs. But today he'd probably say Algorithms plus Data Structures are predictions. So thanks very much.